is we need to, first of all, understand what an equation of a circle is and how to graph a circle. Recall, that was a section that we did skip way back. All right, and so it's kind of coming back to haunt us, but it's not a big deal. It's easy to pick up on a circle. So we will start off by looking at the equation of a circle. This is the equation of a circle in standard form. Okay, where the center of the circle can literally be read off from the equation. It's the ordered pair HK. And the radius of the circle is the square root of r squared, or r. So if I have this equation here, x squared plus y minus 3 squared equal to 25. This is the equation of a circle. And the center of this circle would be at 0, 3. That would be the center. And the radius would be equal to 5. Okay. Now that you know the center and the radius of a circle, it's very easy to graph the circle. So the center is going to be at 0, 3 up here. And then the radius will be 5 units in all directions. Okay, so all right, so the radius is 5. 5 that way, 5 this way, 5 this way, 5 this way. Okay. So the key is knowing what the equation of a circle is. And if this was instead of y minus 3, if it was y plus 3, then the y coordinate of the center point would be -3. Okay. All right, so that's the equation of a circle, and hopefully you can remember that. And once you do remember this, graphing a circle is pretty easy. You can just determine the x coordinate and the y coordinate of the center point, and then you know the radius is a square root of whatever number this is over here. And that should be enough to graph your circle. Parabola. Let's review the equation of a parabola. And of course, quadratic functions generate parabolic graphs. And we've seen that the equation of a parabola in vertex form was this. This was a ways back though, so that's why I'm reviewing this. This is the equation of a parabola, and this equation is in vertex form, or sometimes we call this standard form. The vertex point is the ordered pair HK. And keep in mind, if like this A is greater than 0, the parabola will open upwards. If A is less than 0, the parabola opens downwards. Okay. All right. So that's the equation of a parabola that opens upwards or opens downwards. Let's see, anything else we need to know here? If you have, let's look at some absolute value functions. Of course, if we have y is equal to the absolute value of x, the graph of this is going to be a V-shaped graph. And the xy plane. If you put a negative in front of the square root of, the absolute value of x, this causes the graph to be reflected about the x-axis. So now your graph will be a V-shaped graph opening downwards. We've seen this before. Nothing new there. Any question about anything on this page here? All right, let's see here if we got, okay, let's see. Ladies and gentlemen, what if we have the equation x is equal to the absolute value of y? The absolute value of y. Well, the graph of this is going to be a V-shaped graph, but this V-shaped graph is going to open to the right. So the graph of the basic absolute value function, which is solved for x and has the absolute value of y, would be a graph that opens to the right. If you have x is equal to negative the absolute value of y, now this is going to be the V-shaped graph opening to the left. All right, so it's just nice to know a couple of these here. All right, so I'm just pointing some of these things out here, so we can hopefully remember some of these things. All right, so let's begin to work in section 5.5 now, solving inequalities involving two variables. So section 5.5, this is the last section we're doing in chapter 5. We are not going to do 5.6. Inequalities and systems of inequalities in two variables is the entitlement of section 5.5. And again, ladies and gentlemen, I would strongly recommend that you just kind of, go through and look at some of these examples that your author is demonstrating. I think that would be extremely helpful to complement what it is I'm going to go over in class here. All right. I purposely do not do any examples out of the sections because I leave those for you to view. Problems I work on are usually even and some odd problems on your homework section, but there's a lot of great examples being displayed here and being solved by your author. Please do take the time to look over some of these examples in section 5.5 to gain a good grasp of what's going on in this section. It's very worthwhile to look at something like that. Right? All right, let's just jump on down here and start looking at some of these problems here. Problem number 7, and they just want you to determine whether the ordered pair is a solution to the inequality. So now they're giving you an inequality in two variables, x and y. And they're just going to ask you if some ordered pairs are solutions to the inequality. So for problem number 7 here, the inequality they give us in two variables is 3x plus 4y is less than 12. A solution to this inequality is going to be an ordered pair that satisfies this inequality. And the first one they want you to check out is this ordered pair -1, 3. So they're asking us, is -1, 3 a solution? Is it a solution to this inequality? And to answer that question, ladies and gentlemen, all we have to do is verify. So in for the x variable goes the x coordinate. In for the y variable, we substitute the y coordinate of the ordered pair, and then we verify. Do we get a true or false statement here? So is 3 times -1 plus 4 times 3, is that less than 12? Is that true or false? Well, 3 times -1 is -3, 4 times 3 is 12. Is that less than 12? -3 plus 12 is 9. Is 9 less than 12? The answer is yes. So therefore, we would conclude that -1, 3 is a solution of the inequality 3x plus 4y is less than 12. So it is a solution. It satisfies the inequality. Any questions how we verified that -1, 3 is a solution to that inequality in two variables, x and y? All right. Is 5.1 a solution to that inequality? Well, One way to find out. Replace the x variable with 5, the y coordinate, excuse me, the x coordinate. And replace the y variable with the y coordinate of 1. So is 3 times 1 times plus 4 times, this should be 3 times 5. Is 3 times 5 plus 4 times 1 less than 12? Is that true? 3 times 5 is 15. 4 times 1 is 4. Is 15 plus 4 less than 12? Is 19 less than 12? The answer is no. So therefore, we would conclude that 5, 1 is not a solution to this inequality. Any questions how we're basically verifying whether an ordered pair is a solution to an inequality in 2 variables? Any questions how we're going about doing this? Pretty simple task. Just replace the x variable with the x coordinate and replace the y variable with the y coordinate. And if upon simplifying, you discover that you get a true statement, then the ordered pair is a solution to the inequality. If you get a false statement, the ordered pair is not a solution to the inequality. All right, any questions how we're doing a problem like this? Just verifying whether an ordered pair is a solution to an inequality in 2 variables. All right, so that's all they're having you do in these early problems here, 7 through 10. They're just going to give you an inequality. Notice some of these inequalities are nonlinear, like number 9 is a nonlinear inequality, actually called a quadratic inequality in x and y. And number 10 is a quadratic inequality in x and y. But nonetheless, to confirm whether an ordered pair is a solution, just replace the x variable with the x coordinate, the y variable with the y coordinate, and then verify. Do you get a true or false statement? If it's true, the ordered pair is a solution. If the statement's false, the ordered pair is not a solution. Need I say any more about that? Any questions about that? Anybody have any questions about this so far? All right. Now, in these problems, they want you to graph the solution set to these inequalities. So like problem number 14 here, they want us to graph the solution set of this inequality. Now, why would we want to graph the solution set to this inequality? Well, if this inequality has any solution, it must not be just a number, because this inequality has 2 variables in it. It has to be an ordered pair. And the ordered pair solution has to satisfy the inequality. Well, I'll let you in on a little secret, Liz. These inequalities in 2 variables don't just have one ordered pair solution. They have an infinite number of ordered pair solutions. And so for that reason, there's no way we can enumerate all of the ordered pair solutions, because there is too many of them. For that reason, we need to graph the solution set in the XY plane. So let's look at this simple inequality in 2 variables, x and y, and see how we would solve it by graphing its solution set into the XY plane. All right, so we're going to try to do problem number 14 here. And the first thing we need to do in order to solve an inequality in 2 variables is we need to graph the associated equation first, because we have to know where on the XY plane the boundary lies. So the first thing we need to do to graph the solution set of this inequality step number 1, we need to graph the associated equation by replacing the inequality with the equal sign. We need to graph this linear equation first. Now, how are we going to graph this linear equation? There's many, many ways to graph a linear equation. We could use the table method. We could use the XY intercept method. We could get this equation in the slope-intercept form and then graph it from that form. I think what I'm going to do is get this in the slope-intercept form. So, solving for y, to put the equation into slope-intercept form. How do we solve for y? Help me solve for y, anybody?
Move the negative 5x to the other side. Well, I guess add plus 5x to both sides.
Let's add 5x to both sides. That'll kick it over to the right. Equal sign equals 8 plus 5x. So we add 5x to both sides. The 5x's drop out on the left, leaving you with 4y equal to 8 plus 5x. Now we're going to divide both sides of the equation by 4. I'm going to spin these terms around here. We're shooting for slope-intercept form. Hence, we have y is equal to 5/4 x plus 8 divided by 4 is 2. So now we got our equation in the slope-intercept form. So therefore, the slope of this line is going to be equal to 5/4, and y-intercept is equal to 2. So knowing that information, we can graph this line in the XY plane. To do that, we take ourselves a piece of graphing paper, ladies and gentlemen, and a ruler wouldn't hurt. So I'm going to try to graph y equals 5/4 x plus 2. To do that, we will plot the y-intercept first, which is plotting 2. There's the y-intercept right there, 0, 2. And now we're going to use the slope to plot other points on the line. The slope says for a rise of 5, we have a run of positive 4. So if from my y-intercept I go up 5 units and then go 4 to the units to the right, I'll plot another point on this line. So 1, 2, 3, 4, 5, and then 2 to the right, 4 to the right, excuse me. There we go. Or I could have viewed my slope as -5 over -4, in which case I go down 5 units and 4 to the left. I would still locate another point on this line. So from my y-intercept, I'll go down 5, 1, 2, 3, 4, 5, and then 4 to the left. -1, -2, -3, -4. There's another point on my graph there. All right. Okay, so now we're going to put a line through these points, but hold on a second. When we're solving inequalities in 2 variables, we need to remember this. If you ever have the equal sign in your inequality, if you have a less than or equal to or greater than or equal to, we always use solid. We always use a solid line or curve, whatever the case might be, if you have a nonlinear relationship. If you have the strict inequality, strictly less than or strictly greater than, then you always use a dashed line or curve. All right, notice in our inequality, we have the equal sign as part of our inequality. Therefore, we're going to put a solid line through our points we plotted, not a dashed line, solid line. So therefore, we're going to put a solid line through these points. And we have clearly graphed the boundary that will basically separate the solution plane from the non-solution plane. Along this line, I'm going to put the equation that generated it. That way I know, from whence it came. All right, so all I did so far is with this inequality in x and y is I graphed the associated equation. And the graph of the equation is a line. Now, the next step in this procedure, ladies and gentlemen, is we need to determine on what side of the line we shade. In other words, to locate the other ordered pair solutions of this inequality, in addition to the ones that lie on this line, we need to choose a convenient test point, either in this plane down here or this plane up here. It doesn't matter whether you choose a test point in this plane or in this plane, take your pick. Normally, I always use the origin, which is 0, 0, as my test point. 0, 0 is a convenient point to work with. So what I'm going to do is I'm going to test out 0, 0 in my inequality, which is negative 5x plus 4y less than or equal to 8. Now, why are we testing out 0, 0? Well, we're going to determine if 0, 0 is a solution to the inequality. So, is the ordered pair 0, 0 a solution? Is it a solution to the inequality negative 5x plus 4y less than or equal to 8? To answer that question, I replaced the x variable with 0 and the y variable with 0. So is negative 5 times 0 plus 4 times 0, is that less than or equal to 8? Is that true or false? The left side goes to 0. Is 0 less than or equal to 8? True or false? That's true. So what did we discover? Hence, 0, 0 is a solution of our inequality, negative 5x plus 4y less than or equal to 8. So, therefore, we are going to shade the plane that contains 0, 0. We shade the plane that contains 0, 0 because we discovered 0, 0 is a solution to this inequality. So what plane am I going to shade? What side of the line am I going to shade? Am I going to shade the plane below and to the right or above and to the left? What do you think? What plane contains 0, 0, my test point that I chose?
Below to
and
the
to the
right.
right.
0, 0 is in the plane below and to the right of this line. So we're going to shade this plane here below and to the right. And ladies and gentlemen, you're looking at the graph of the solution set to this inequality in x and y. Any point that lies, any point or ordered pair that lies in the shaded region, and there's an infinite number of them, would be a solution to this inequality. Or any point that lies on this line, since it's a solid line, would also be a solution to this inequality. Any point that lies in this plane above and to the left of the line would not be a solution to this inequality. So in addition to 0, 0, can somebody give me another solution to this linear inequality? We know 0, 0 is a solution. Can you give me another solution?
0,
Happy?
-1.
0, -1 would be a solution because it lies in the shaded region. Can you give me another one? Do you think 10, 0 would be a solution way out here? Yeah, it's in the shaded region, correct? Would this point up here be a solution to the inequality? That point right there? You think this is a solution?
No.
No. So, do we understand how we went about, ladies and gentlemen, graphing the solution set to this inequality in x and y? To recap quickly, what did we do? First, we had to graph the equation. We did so by putting the equation in the slope-intercept form and then graphing the line from that. Once we graphed the line or the equation, we had to then decide on what side of the line to shade to round out the rest of our solution set of ordered pairs for this inequality. To do that, we chose a convenient test point clearly on one side of our line. I chose 0, 0. It's the easiest point to work with. And we discovered that 0, 0 is indeed a solution to the inequality. Being the case, we shaded the plane that contained 0, 0. If we went through this and discovered that 0, 0 was not a solution to the inequality, then we would be shading the plane on the opposite side of the line. Does this make sense at all? Anybody got any questions how we solve this inequality in X and Y using our graphing method? All right. So graphing paper probably would come in handy. Do you agree when you're solving these inequalities? All right, well, let's try another one there. That one's done, number 14. Okay. Let's see what other one we got here. All right, one like number 24. We want to graph the solution set of this inequality. Now, ladies and gentlemen, we're not seeing which variable in this inequality here. What variable is missing?
Y.
Y. So to solve this inequality by graphing, the first thing we need to do is we need to graph the associated equation. So we need to graph 1/3 x plus 2 equals 4. That's the first step. So how are we going to graph this linear equation that only has one variable in it? What kind of a line do you think this equation is going to generate if it just has the x variable? Do you remember?
Undefined?
What's that?
Would it be an undefined line or horizontal?
Okay, I'll give you a hint. It's either going to be a horizontal or a vertical line. Which one is it going to be?
Vertical.
It's going to be a vertical line because we don't have the y variable. So solving for x, we subtract 2 from both sides. We get negative 1/3 x is equal to 2. Multiply both sides by negative 3. Negative 3 times its reciprocal, negative 1/3 is 1. So negative 3 times negative 1/3 x is x. Negative 3 times the right-hand side 2 is negative 6. So ladies and gentlemen, what's the graph going to be for x equals negative 6? It's going to be what kind of a line?
Vertical line passing through -6?
Yes. So it's going to be a vertical line passing through the x-axis at -6. So, and would it be a solid or a dashed line?
Dash line?
Yeah, because we have a strict inequality here, ladies and gentlemen, we're going to have a dashed line, not a solid line. So we're going to graph a dashed line going to the x-axis at -6. So negative 1, 2, 3, 4, 5, 6. So it's going to be a vertical line right through here, and it will be a dashed line. Okay. Everybody understand how we graph, first of all, the equation? Second step now is we need to determine on what side of our line to shade, what plane to shade. To determine that, we choose a test point, convenient test point. The nicest test point to work with of all the points in the XY plane is 0, 0, the origin. When could I not choose 0, 0 as a test point?
If it passes through the line.
If the graph of the equation passes right through the origin or contains the origin, then you cannot choose 0, 0 as a test point. You would have to choose some other point clearly on one side of the line. But 0, 0 is available here. So what we're going to do is we're going to see if 0, 0 is a solution of our inequality, negative 1/3 x plus 2 less than 4. We need to see if 0, 0 is a solution to our inequality. So to do that, we let x be 0, y be 0, substitute them into our inequality for x and y. And we ask ourselves, is negative 1/3 times 0 plus 2 less than 4? Well, negative 1/3 times 0 is 0, and 0 plus 2. 0 plus 2 is 2. Is 2 less than 4? True or false?
True.
True. So that being the case, ladies and gentlemen, we conclude that 0, 0 is a solution of the inequality. Negative 1/3 x plus 2 less than 4. So we therefore shade the plane that contains 0, 0. If we discovered 0, 0 is not a solution to this inequality, we would shade the plane that does not contain 0, 0. So where am I going to shade? Am I going to shade to the right of this vertical dashed line or to the left?
Right.
To the right. The plane to the right contains 0, 0. We just discovered 0, 0 is a solution to the inequality. That's enough to say that all points to the right of this vertical dashed line are solutions to the inequality. So we shade to the right. And ladies and gentlemen, you have the graph of the solution set to this inequality in x and y, negative 1/3 x plus 2 less than 4. Any point that lies in this shaded region would be a solution to this inequality. I got a question for you. What if I choose a point actually on this vertical dashed line? Would it be a solution to the inequality?
No.
No, because this is a dashed line. Dashed lines mean that points on the line or the curve are not solutions to the inequality. Only points shaded to the right of this vertical dashed line would be solutions to that inequality. Okay. So can anybody give me a solution to this inequality other than 0, 0?
7, 6.
Yeah, 7, 6. 7, 6 is definitely in the shaded region over here. So any point to the right of this vertical dashed line would be a solution to that inequality. It's making sense how we're solving inequalities by graphing their solution sets. How we're solving inequalities in two variables by graphing their solution sets in the XY plane. Okay. All right, that was number 24. Maybe we can try another one here. Let's see. Go back to our textbook. All right, let's see. All right, let's try this one. Number 26A, we want to graph the solution set of this quadratic inequality. Notice that's no longer a linear inequality, that's a quadratic inequality. So 26A, these problems are at the end of section 5.5 in your textbook. So we're going to try to graph the solution set of y greater than or equal to x squared minus 1. So what's the first step? What do you think I do first? What have I done? What's the first step, ladies and gentlemen?
Change the greater than to an equal sign and graph the equation.
All right, first thing we got to do is we got to graph the equation. If you don't graph the equation first, you're not going to have a clue where the boundary is in the XY plane. Got to graph the associated equation first. Notice this is not a linear equation anymore, so its graph is not going to be a line. In fact, it's a quadratic equation. So its graph is going to be a parabola. Is this quadratic function in vertex form? Well, after a little thought, hopefully you'll discover that it is. I can rewrite y equals x squared minus 1 as 1 times x minus 0 quantity squared plus a negative 1. You can clearly see that this quadratic function is in vertex point form. So what's my vertex? It's the ordered pair HK. What would it be? What's my vertex point? What's H? H is 0. What's K? Negative 1. That's your vertex point. Does this parabola open upwards or downwards? What's A? A is what?
A is positive, so it opens upwards.
A is positive 1 greater than 0. Therefore, the parabolic graph will open upwards. That's going to render that vertex point as being a minimum point on the graph. Do you agree? All right, so what we're going to do is we'll take our graphing paper. Now, if you want a very accurate graph, instead of just a sketch, then you might want to try to find any x-intercepts or maybe y-intercepts. That will give you a much more accurate graph. So how do we find x-intercepts? What do I always set equal to 0 to find an x-intercept?
Y.
Take 0, substitute in for the y variable right here, y. I'll use the equation. So therefore, our equation collapses down to 0 equal to x squared minus 1. Now, how do we solve this quadratic equation for its two solutions? You could do this one of two ways. You could factor the left side, use the factoring method, or you could add 1 to both sides and take the square root and use the square root method. It doesn't matter. Okay. If you want to factor the left side being the difference of squares, it factors in x minus 1 times x plus 1. Setting your factors equal to 0, solving for x, we discover that we have two x-intercepts. What are they? Two x-intercepts, one at 1 and one at negative 1. So your x-intercepts are negative 1, 0 and 1, 0. Those are your x-intercepts. Just find the y-intercept. What do I set equal to 0? Find the y-intercept.
Set x equals 0.
X gets set equal to 0. Take 0, substitute in for x, and then solve for y. Hence, our equation is going to be y equal to 0 squared minus 1. Y is equal to 1. Your y-intercept is 0, 1. Now, ladies and gentlemen, we know our y-intercept, our x-intercepts. We know the parabolic graph opens upwards. We know the vertex point. I think that's more than enough information to draw an accurate graph of this parabola. Let's take a piece of graphing paper and plot what we know.
Wouldn't it be
Well,
0, negative 1?
Yeah, because the
Yeah, you're right. Yeah, thank you. Yep, 0, negative 1. All right, so let's plot what we know. Now, not only is our vertex point a minimum point, but the vertex point turns out to be the what intercept?
Y-intercept.
Happens to be y-intercept. Notice that. Just so happens that's the way it is for this parabola. So plotting the vertex point at 0, negative 1, that also happens to be the y-intercept. The x-intercepts we determine algebraically were 1 and negative 1. Plotting the x-intercepts, 1, negative 1. The graph opens upwards. Ladies and gentlemen, is this going to be a solid curve or a dashed curve? Solid or dashed curve?
solid.
Yeah, because we have the equal sign as part of an inequality, we're going to use a solid curve. Hence, here comes our parabolic graph using a solid curve. All right, so we graphed our equation, which is a parabola opening upwards. Now, the second major step of this problem is we have to determine whether we shade inside the parabolic branches or outside the parabolic branches to round out the rest of the solution set to this quadratic inequality. So what we're going to do is we choose a test point. Which one have I always chosen?
0, 0.
Is 0, 0 available here? It certainly looks like it, since our graph does not go through the origin. The origin is available for a test point. So we ask ourselves, is 0, 0 a solution of the inequality y greater than or equal to x squared minus 1? Is it a solution? We're going to find out. We're going to find out. We're going to replace the y variable with 0 and the x variable with 0. So is it true that 0 is greater than or equal to 0 squared minus 1? Is that true or false? Is 0 greater than or equal to -1? True or false?
True.
True. So what have we discovered? So 0, 0 is a solution of the inequality y greater than or equal to x squared minus 1. Hence, we shade the plane that contains 0, 0, because we discovered it's a solution. Which means, ladies and gentlemen, that we're going to shade in between the branches of the parabola, because it's that plane that contains 0, 0. So therefore, the graph of the solution set to this quadratic inequality is going to be all ordered pairs that lie in the shaded region inside the branches of the parabola. And of course, these branches go upwards forever, so does the shading. Any point that lies in the shaded region inside the parabolic branches or on the parabolic graph itself will be a solution to this quadratic inequality. And we're done. Questions how we solved this quadratic inequality, how we graphed its solution set. Any questions with what we just accomplished here? First, you got to graph the equation always. Once you graph the equation, then you choose a convenient test point, and you have to test where you're going to shade to determine the rest of the solution set. Does anybody have a question why we shaded inside the branches of the parabola? We did so because we found out that 0, 0, which lies inside the branches, is indeed a solution to our inequality. It's a solution. If we discovered 0, 0 was not a solution, we would not be shading inside the branches. We would have shaded outside. Okay. All right. Any questions, ladies and gentlemen, how we're solving these inequalities involving two variables, x and y, by shading or graphing the solution set? All righty. All right, let's see here. Now for 26b, it says, explain how the graph would differ for the inequality y less than or equal to x squared minus 1. Ladies and gentlemen, if I flip the inequality symbol around from where it says y is greater than or equal to x squared minus 1 to saying y is less than or equal to x squared minus 1, how would that affect the solution set? Where
You would
I
shade on the other side.
That's right. If I had the inequality y is less than or equal to x squared minus 1, instead of what we graphed, y greater than or equal to x squared minus 1, then we would be shading what? Outside the parabolic branches. Do you agree? That would be the solution set of y being less than or equal to x squared minus 1. We would shade outside. About 26c, explain how the graph would differ for the inequality y strictly greater than x squared minus 1, as opposed to the one we solved, y greater than or equal to x squared minus 1. What would be the difference in the solution set?
Just a dotted line instead of a solid.
Yes, the only difference is with 26C, we don't have the equal sign in our inequality. And because y would be strictly greater than x squared minus 1, the only difference between the graph of the one we solved, where y is greater than or equal to x squared minus 1, to that one, is we would have just a dashed curve indicating the boundary of our parabola, a dashed curve. The shading would still be inside the branches though. Is that making sense here for problem 26? All right. Okay, so ladies and gentlemen, classwork number 1 is problem number 27 here. Classwork 1, today is the 15th day of November. I think it's the first day of deer hunting season, isn't it? Firearm season? Yeah, just be careful if you're driving on the roads, ladies and gentlemen, as deer will be on the move. They're especially on the move at nighttime. Be very careful. 2 years ago, I was driving home 23 northbound from Ann Arbor about 9 p.m. just north of Heartland. I was going 70 miles an hour in the right lane, doing the speed limit. And within 1 second, a deer bolted out from the median and slammed right into my headlight. It happened within 1 second. I had no choice to do any sort of evasive action whatsoever. So I just kept driving. You know, the deer slammed in my headlight, caromed off the side of my van, and I don't know what happened to the deer. Luckily, there was no other cars or vehicles around me. I just kept driving. Screwed my whole front quarter panel up, though. I had to take it to a collision shop. Yeah. So be careful. Deer are on the move. Dangerous time of the year, especially at nighttime. All right, ladies and gentlemen, I would like you to try to graph the solution set for problem number 27, which says y is less than negative x squared. I'm going to have you just play around with this problem and see what you can do with it. Now, warning. I normally have chosen 0, 0 as the test point. Ladies and gentlemen, I don't think you're going to have this luxury of choosing 0, 0 as being your test point, because I think the graph of this quadratic equation is going to go through the origin. So you're going to have to choose some other point. Just see if you can do this problem, okay? Number 27, classwork number 1. All right, now, step number one is we want to graph the equation. Now, we know that the graph of the basic quadratic function, the most basic one, y equals x squared, we know is a parabola that opens upwards, the vertex is at the origin, correct? What happens when you put a negative in front of a function? What does it cause the graph of the basic function to do?
Flip around the x-axis.
That's right. It causes the graph to be reflected about the x-axis. So therefore, your graph is going to be literally a parabola opening downward. Vertex point at the origin. Would it be a solid or a dashed curve?
Dashed.
Dashed curve. Opening downwards. There you go. This would be the graph of your parabolic boundary. And you just have one more step to undertake here. You just have to determine whether you shade inside the parabolic branches or outside to indicate the solution set of all ordered pairs for this inequality. Notice, unfortunately, 0, 0 is not available as a test point. You have to choose some other point, either clearly outside of the parabolic branches or inside. I'm going to choose a point inside the parabolic branches. I'm going to choose the point 0, -5 here as my test point. Okay, so therefore, using 0, -5 as a test point, I ask myself, is 0, -5 a solution of the inequality y less than x squared? Well, let's find out. We'll replace the y variable with the y coordinate, replace the x variable with the x coordinate. So is -5 less than 0 squared? Is that true? Is -5 less than 0?
Yes.
That's true. So therefore, we have discovered that 0, -5 is a solution. It's a solution to y less than -x squared. That being the case, ladies and gentlemen, we have to shade the plane that contains 0, -5, which means we have to shade inside the parabolic branches. If we discovered that 0, -5 was not a solution, we would have to shade outside the parabolic branches. Or maybe you chose a test point outside of the parabolic branches. Did anybody choose a test point outside the branches? Anybody? Okay. Did you discover that that point was not a solution?
Yes, it is.
Exactly. So if you choose a point that's not inside the parabolic branches, you'll discover it's not a solution to the inequality, which is forcing us to shade inside the parabolic branches. And there you go, ladies and gentlemen. Hopefully you all got this problem correct here. This would be the graph of the solution set to this inequality involving two variables, x and y. Any point that lies in this shaded region would be a solution. Notice a point that actually lies on the parabolic boundary would not be a solution because this is a dashed curve, not a solid curve. If I change this from less than to less than or equal to, how would that change my solution set? If I just put the less than or equal to, how
A
would that
solid
change?
line.
It would be a solid curve then, correct? The parabolic boundary would be a solid curve instead of a dash curve. All right. What if I flip this inequality around and said y is greater than -x squared? Where would I shade then?
The outside of the
It would
parabola.
have been shaded on the outside, exactly. All right. Is this making sense so far how we're solving inequalities involving two variables, x and y, by graphing the solution set in the plane? All right. Let's go on here and wait a minute. What just happened? Oh, okay. All right, that was 27. That's classwork number 1. Let's move on here. Time is burning here. All right, one like number 28. They want us to graph the solution set of this equation, or excuse me, this inequality. Do you recognize what the equation is going to be? Number 28. Okay, so what we're gonna do is we're gonna try to solve by graphing the solution set. All right, first we have to graph the equation. Step number one, must graph the associated equation. Does anybody recognize what kind of graph this is going to generate?
A circle.
It will be a circle. And if we want to write the circle's equation in strict standard form, we can certainly do that. So, ladies and gentlemen, what's going to be the center of the circle? What's my center of my circle? It's going to be the origin, isn't it? 0, 0, 0, 0. This is the x coordinate of the center of the circle. This is the y coordinate. What's the radius going to be? It's going to be the square root of 16, or it's going to be just what? 4. That's your radius. That should be enough information to graph this circle in the xy plane, knowing the center and the radius. Take a piece of graphing paper. And let's see if we can graph this circle here. So we know the center is at the origin, 0, 0. We know the radius is 4, so that means out here, there will be a point on our circle. Up here, there'll be a point. Over here, there will be a point, and down here, there will be a point. Now we can pencil in our circle. Obviously, a compass would make for a perfect circle. I don't have a compass, so I'm going to have to be careful. So wish me luck in drawing my circle. I'm having a heck of a time trying to draw this circle. Like I said, a compass would be the way to go. That's not too bad. I've drawn worse circles. It's not perfect, but you get the idea. That would be the graph, ladies and gentlemen, of x squared plus y squared equals 16. That's its graph. The radius is 4. Everybody see that there? The radius is the square root of 16. The center of the circle is at the origin. Now, the only other step now is we just have to determine whether we shade the plane inside the circle or shade outside of the circle to determine the solution set to this inequality in x and y. To answer that question, we choose a convenient test point. Is 0, 0 available here?
No.
Why not? Does my graph go through 0, 0?
Oh, wait, no, it doesn't.
No, the circle doesn't go through 0, 0. I mean, that is the center of our circle, but don't worry about that. As long as our graph doesn't go through the center, it's available. So we're going to choose 0, 0 as a test point. And so we ask ourselves this question: is 0, 0 a solution? Is it a solution of the inequality x squared plus y squared greater than or equal to 16? We need to answer this question. Well, to answer that question, we replace the x variable with the x coordinate of 0, replace the y variable with the y coordinate. So is 0 squared plus 0 squared greater than or equal to 16? Is that true or false? Is 0 greater than or equal to 16? That is false. So we have discovered that 0, 0 is not a solution of our inequality, x squared plus y squared greater than or equal to 16. So we shade where? Where do we shade? Since 0, 0 is
Outside
not a
of the
solution.
circle.
What's that? Inside?
Outside.
So we shade outside the circle to denote the solution set of this inequality, because 0, 0 is not a solution. It does not satisfy the inequality. So therefore we shade outside. And ladies and gentlemen, we have graphed the solution set of x squared plus y squared being greater than or equal to 16. Any ordered pair that lies essentially outside the circle will lie in the solution set of this inequality, and we're done. That's the solution set. We graphed it. Any point that lies on the boundary, actually on the circle, would also be a solution to the inequality. But any point that lies inside the circle would fail to be a solution to this inequality. That makes sense how we did that problem there, like where we have a circle here. Okay. All right. That making sense there so far? Okay, good. All right, so far, ladies and gentlemen, we've only had one inequality to graph a solution set for. What if we had a system of inequalities in two variables, x and y? What if we had a system? Like number 39, ladies and gentlemen, illustrates what's called a system of two linear inequalities in two variables, x and y. It's a system now. And any solution to this system has to be an ordered pair that satisfies both inequalities simultaneously. If an ordered pair fails to satisfy any one of these inequalities, it will not be a solution to the system. So let's look at number 39, the system of two linear inequalities and two unknowns. And let's ask ourselves this question here as we strive to do problem 39b. Is the ordered pair 3, 1 a solution to this system of two linear inequalities, x plus y being less than 4 and y being less than or equal to 2x plus 1? Do you think that ordered pair 3, 1 is a solution to this system? Well, to answer that question, we have to test it out. Test it out in both inequalities. We got to test it out in both inequalities. So first we'll test it out in the first one. X plus y less than 4. So we're going to replace the x variable with 3, the y variable with the x variable with 3, the y variable with 1. And we ask ourselves, is 3 plus 1 less than 4? Is that true or false? Is 4 less than itself? That's false. We don't even have to bother in testing 3, 1 out in the other inequality. We don't care. It fails to satisfy the first one. And so the answer is no. 3, 1 is not a solution to this system. To the system. To be a solution, it has to satisfy both inequalities simultaneously. Everybody understand how we would determine whether an ordered pair is a solution to a system of inequalities and two unknowns? To be a solution, it has to satisfy both inequalities. If it fails to satisfy just one of them, it's not a solution. So that's not a solution. All right, let's move on. Now, ladies and gentlemen, this is probably problem number 41. It says, graph the solution set of this system of two linear inequalities and two unknowns, x and y. We're going to try to graph the solution set. If there is no solution, indicate that the solution set is the empty set. All right, so we have to graph the solution set of this inequality, system of inequalities in two variables, x and y. And how do you think we would do that? How do you think we're going to do this problem here?
Would we graph both equations and then just test each area that the lines create by crossing one another?
Yeah. So basically what we're going to have to do here, Lizone, is, okay, to solve this system of two linear inequalities and two variables, the first thing we're going to have to do is we're going to have to graph each of these associated equations first. So first of all, we're going to graph the equation y equals to 1/2 x minus 4. Let's graph this one first. Notice this linear equation is in what form? What form is this in? That's in slope what? Slope intercept form? So let's graph this equation using a piece of graphing paper here. Please do use graphing paper for accuracy. So to graph y equals 1/2 x minus 4, where the slope is 1/2 and the y-intercept is -4. First, we plot the y-intercept, which is at -4 down here. And now the slope is 1/2, so a rise of 1, a run of 2. So a rise of 1 and a run of +2. There's another point on our line. Go up again, rise of 1, run of 2, another point on our line. Do I put a solid or a dashed line through these points? Solid or dashed line? We got strictly less than, so we put a dashed line through these points. So we take a ruler and we're going to put a line through these points here. It's going to be a dashed line. There you go. That's the graph of the first equation, y equals 1/2 x minus 4. Along this line, I'm going to put the equation that generated it so I know like where it came from, all right? It's just nice to know what equation generated which graph. So just pencil in the equation right along the line somewhere. Now, ladies and gentlemen, what we need to do is we need to determine on what side of this line we shade. Do we shade the plane below and to the right or above and to the left? To round out the rest of the solution set to this inequality. So the next step is we choose a test point. And you know which one I like. 0, 0. And 0, 0 is available here because my line does not pass through 0, 0. So choosing a test point 0, 0, we ask ourselves, is 0, 0 a solution? Is it a solution to my inequality, y being less than 1/2 x minus 4? To answer that question, we replace y with 0, replace x with 0. And we ask ourselves, does 0, 0 satisfy the inequality? Is this true? Is 0 less than 1/2 times 0 is 0? Is 0 less than 0 minus 4? Is 0 less than -4? Is that true or false? What do you think?
False.
False. So therefore, we've discovered that 0, 0 is not a solution. It's not a solution of y less than 1/2 x minus 4. So because it's not a solution, ladies and gentlemen, we shade the plane that does not contain 0, 0. So where am I going to shade? Do I shade the plane above and to the left or below and to the right?
Below and to the right.
Yeah, we don't shade above and to the left because that plane contains 0, 0, which we determine is not a solution. So we got to shade below and to the right. And ladies and gentlemen, since we're going to be graphing solution sets to 2 inequalities in x and y, this is where a different colored pencils or different color markers would come in handy to help you better see the overlap between the shaded regions, as I've given a hint to you as to what our solution set's going to be. I don't have colored pencils and crayons or markers, so I just kind of go like this. We have graphed the solution set to just the first inequality in our system. We now have to graph the solution set to the second inequality in our system, this one. Now we have to take care of this one. So we got double trouble with the system. So now what we're going to do is we're going to graph the associated equation for the second inequality. We have to graph y equals -2x plus 1. This equation's also in what form? What form is this? Y equal to mx plus b form, slope-intercept form. So what's the slope of my line?
-2.
-2/1, or you could say 2/-1. It's up to you. What's my y-intercept?
1.
0, 1. Okay, that should be enough information to graph the second equation. So let's take it to the plane now, plot our y-intercept, and using the slope, plot some more points to derive the graph of that second equation. So we go to our xy plane, we plot the point 0, 1. 0, 1's right here. There's my y-intercept. Now, using my slope, which is a rise of -2 and a run of +1, we should be able to plot more points on our line. Going from my y-intercept to 0, 1, I go down 2 units, -1, -2, and then over 1 to the right. We could do that again. Down 2, over 1 to the right. Down 2, over 1 to the right. Take a ruler out. What kind of line do I put through these points? Solid or dashed? It would be a dashed line. So take a ruler, put a dashed line through these points. And ladies and gentlemen, you have graphed the second equation. And along the second equation, I'm going to put the equation that generated it. Y is equal to -2x plus 1. Now, the only other thing that remains now is we just have to determine whether we shade the plane below and to the left of this dashed line, this plane, or do we shade the plane above and to the right, this plane? And then we'll be done. To answer that question, we need to choose a convenient test point and test it out in our second inequality. Notice 0, 0 is available just by a smidget though. 0, 0 does lie in the plane below and to the left of this dashed line here. So 0, 0 is available. So here we go. Test 0, 0. In the inequality, y greater than -2x plus 1. So we replace the y variable with 0 and the x variable with 0, and we verify true or false statement. Is 0 greater than -2 times 0 plus 1? Is that true or false? Is 0 greater than 1? Is that true? Is 0 greater than 1? False. So 0, 0 is not a solution of this second inequality. Hence, we shade what plane? What plane am I going to shade? The one that's below and to the left of this dashed line or above and to the right? Which plane do we shade?
Above and to the right.
The plane that's above and to the right, because that's not supposed to be the plane that contains 0, 0. We showed that 0, 0 does not satisfy the second inequality. You cannot shade the plane below and to the left. Hence, we shade the plane above and to the right of the graph of y equals -2x plus 1. So later we shade this away. And you have graphed the solution set of the second inequality. Ladies and gentlemen, I have a question for you. What then do you think is going to be the solution set to this system of 2 linear inequalities and 2 unknowns? What's going to be the solution set to the entire system? What's going to be the solution set to the entire system?
The part that overlaps.
That's right. It's going to be where the shaded regions overlap. And that's why colored pencils or markers might be more attractive here. It might make things easier for you to see where the overlap is. I can still see it though. It's going to be right in here. So this would be the graph of the solution set of that system of 2 linear inequalities and 2 unknowns. Any point that lies in this darkened shaded region here would satisfy both inequalities simultaneously, would be a solution to the system. Okay, it has to be a point that lies in this darkened shaded region. Notice it would not be a point that lies on either this dashed boundary or this dashed boundary. No, it's got to be literally just in this darkened shaded region here. And we're done. Questions, ladies and gentlemen, how we graph the solution set of this system of 2 linear inequalities and 2 unknowns. This is problem number 11 in your textbook. To recap, first we had to graph the associated equations and test out and see on what side of the lines we shade. Then, to determine the solution set of the system of inequalities, it's where the shaded regions overlap, constitutes the solution set to the system. And we're done with that problem. Is this making sense how we're solving these systems here so far, Liz, on these systems? That was the first one I showed you. All right, let's mosey on down. Wow, okay, let's look at like number 46 here, Liz. I'm on problem 46. They want us to graph the solution set of this system of two nonlinear inequalities and two unknowns. X squared plus y squared is greater than or equal to 1, and the other inequality is x squared plus y squared is less than 25. How are we going to do this problem? Well, first thing we need to do is graph the equations. We have to know where the boundaries are. So we have to graph x squared plus y squared equals 1. We'll graph that equation, and then we're going to graph this other one, x squared plus y squared equals 25. Must graph the equations first. What kind of graph do you think this equation is going to generate?
Circle.
Anybody? A circle. Where is it going to be centered at? Where is the center of this circle?
0, 0.
0, 0. So the center of this first circle is the origin. And what is the radius of this circle? It'll be the square root of 1, which is what? 1. All righty. Okay. So, ladies and gentlemen, let's take a piece of graphing paper and let's graph that first circle. And by the way, the curve going through the first circle, is it going to be a solid or a dashed line?
Solid.
Solid curve. Do you agree? Because we have the equal sign involved in our inequality. So let's go to our graphing paper. Let's plot the center of the circle is at 0, 0. The radius is what? 1. So there's going to be part of the circle, point on a circle, point on a circle, point on a circle. Let's now pencil in a solid circle containing these points 0, 1, negative 1, 0, 0, negative 1, and 1, 1, 0. That's the graph of our first circle. Now we need to make a determination. Do we shade inside the circle now or outside the circle to determine the solution set of this first inequality? To answer that question, we choose a convenient test point. So the origin is available. So we're going to test out 0, 0 in our first inequality, x squared plus y squared greater than or equal to 1. Let's see, replace x with 0, y with 0. Is 0 squared plus 0 squared greater than or equal to 1? Is that true? Is 0 greater than or equal to 1? That's false. So therefore, we've discovered 0, 0 is not a solution of the inequality x squared plus y squared greater than or equal to 1. So we shade where? Do we shade inside the circle or outside?
Outside.
Yeah, we got to shade outside circle. So the solution set, the graph of the solution set of the first inequality of our system, which is right here, is going to have us graphing what? Outside the circle here. So you are looking at the graph of the solution set of the first inequality. It's going to be any ordered pair that's outside of the circle or on the circle or on the circle. Okay, that's a solid curve there. Any questions how we graph the solution set of the first inequality there? All right, now to graph the solution of the second inequality, first of all, we have to graph the equation. And this is going to be what kind of a graph?
It's another circle.
Another circle centered at the origin with a radius of what?
5.
5. So the center, just like the last circle, is at the origin, 0, 0, 0, 0, and the radius is going to be 5. Solid or dashed curve through the circle.
Dashed.
It'll be a dash curve because we have a strict inequality here. So going back to our graphing paper, ladies and gentlemen, a radius centered at the origin, radius of 5. We're going to have a point on our circle at 5, 0, a point at 0, 5, a point at -5, 0, and a point at 0, -5. Let's put a dash curve to denote this circle here. Good luck. Just do the best you can in graphing this thing. That looks pretty good. Hopefully I can continue that up here. Just do the best you can. Your circles may not be perfect, but just so we get the idea. All right, not too bad. And then my circle is going to come around here, come around, grab that point. That's going to come down here and grab that point. We just have to decide one more thing, ladies and gentlemen. Do we shade inside this dashed circle or outside? To answer that question, we have to test out a convenient test point in our second inequality. And since 0, 0 is available, our graph does not go through 0, 0, we can test it out. So we're going to test out 0, 0 in the second inequality. Replace x with 0, y with 0. Is 0 less than 25? Is that true or false? Is 0 less than 25? True or false? I think this works out to be what? True. Do you agree? And so, ladies and gentlemen, we shade where? We shade inside the circle. X squared plus y squared equals 25. We shade inside the circle because 0, 0 is a solution. Correct? So that being the case, ladies and gentlemen, we shade inside the circle. So where, look at, if we shade inside this big dash circle, do you agree the shading is also going to include the what? Inside the small circle? Do you agree?
Yes.
But do we care about that?
No.
We only care where the shaded regions overlap, and they're only going to overlap what? The shaded regions only overlap literally in between the circles. So the graph of the solution set to that system of two nonlinear inequalities and two unknowns is going to be any point that literally lies in between these two circles. These concentric circles. They're called concentric circles because they share the same center point of 0, 0. They're called concentric circles. Okay. Everybody see that there? So ladies and gentlemen, the graph of the solution set of this system of two inequalities and two unknowns is going to be any point that lies in between the circles. Any point that lies in between the circles. Would that include an ordered pair or point that actually lies on the inner solid circle's boundary? What do you think?
Yes.
You think it does? Now, we know that any point that lies on this inner circle's boundary would satisfy the first inequality, but does it satisfy the second ones? The answer is yes, you are correct. So any point that lies in this shaded region in between the circles or on this solid boundary of the inner circle would be a solution to the entire system of two linear inequalities and two unknowns. This is making sense how we're solving these systems here, ladies and gentlemen. Okay. All right. So that's the solution set for problem number 46, the graph of the solution set. All right. Well, let's see here. Okay, hold on a second here. All right, I'm going to mosey on down here. Let's see if we can do one like problem number 51. You see number 51 here? We have a system of how many inequalities in 51?
3.
There's 3 of them. We're going to try to graph the solution set of this system of three inequalities. Any ordered pair that's to be a solution to this system has to satisfy all three inequalities simultaneously. If it fails to satisfy one of them, it's not a solution to the system. So we're going to try to solve this much larger system now by graphing the solution set. So solve by graphing the solution set. Okay. Well, to do that, we have to graph not one, not two, but three equations, ladies and gentlemen. We have to graph the solution sets of three inequalities. So first, let's take care of the first one. Let's graph y equals x squared minus 2. What is this going to be the graph of? What do you think, ladies and gentlemen? Is this going to be a line? No. It's going to be a what?
Parabola.
A parabola opening upwards or downwards. What do you think?
Upwards.
Upwards, and it basically is the graph of our basic parabola that's shifted downwards, what, 2 units? Do you agree? It's gotten shifted downwards 2 units. All right. Just out of curiosity, what would be the vertex point of this parabola? If I was to write this in vertex form, do you agree that's vertex form? So what's the vertex point? Should be able to read it right off from the equation. It's literally what, 0, -2? That's the vertex point. Would this graph have any x-intercepts? Just curious. How would we find x-intercepts? What do we set equal to 0?
Y.
Therefore, let y be 0. Now we're having to solve this quadratic equation. There's many ways to solve this quadratic equation. Probably the easiest way here is to use a square root method. Let's isolate x squared on the right side by adding 2 to both sides. Now we take the square root of both sides. So therefore, we have x is equal to plus or minus square root of 2. Ladies and gentlemen, we have 2 x-intercepts. One's going to be positive root 2, 0. The other one's going to be negative root 2, 0. Those are your x-intercepts. For plotting purposes, the square root of 2 is about 1.414. So approximately 1.4140 is one of your x-intercepts. The other one will be negative 1.4140. If you're interested in knowing about the y-intercept, we could easily find it by setting x equal to 0. Let x be 0, so y is equal to 0 squared minus 2, which means y is equal to -2. Which means, ladies and gentlemen, our y-intercept is 0, -2, but that also happens to be the what point? 0, -2 is not only the y-intercept, it's also the what point?
The vertex.
The vertex point. It's the lowest point on this graph, agree, as the parabola opens upwards. All right, let's take a piece of graphing paper. And let's graph this parabola here. So we know the vertex point's at 0, -2. We know the x-intercepts are like 1.414 and -1.414. So maybe right about in here and maybe right about in here. Would I have a solid or a dashed curve, ladies and gentlemen, for my parabola?
Solid.
Solid. So hence we're going to have a solid parabola opening upwards here. Okay, now we need to make a determination. Do we shade inside the branches or do we shade outside? To answer that question, we choose a test point. 0, 0 is available. So we're going to test out 0, 0 in the first inequality, y greater than or equal to x squared minus 2. Is 0, 0 a solution to this inequality? Replace x and y with 0 and confirm. Is 0 greater than or equal to 0 squared minus 2? Is 0 greater than or equal to -2? True or false? Is that true or false? That's true. So therefore we shade plane that contains 0, 0. Which means, ladies and gentlemen, we have to shade inside the parabola because it's that plane that contains 0, 0. That's the graph of the solution set to the first inequality in our system. We're not done. We have two more to do though. Now we have to graph the solution set of y greater than x. To do that, first we have to graph the equation y equals x. Ladies and gentlemen, what's the graph of y equals x look like? The second inequality. What's the graph of y equals x?
A horizontal line or no,
It goes up by 1.
Yeah, it's gonna be a line whose slope is 1 and y-intercept is 0. Do you agree? Slope of 1, y-intercept of 0. And it will be what kind of a line, solid or dashed? It's gonna be a dashed line. So here we go. The y-intercept is at 0, the slope is 1. So rise of 1 or run of 1, plot point. 1 up 1 over 1, plot point. Up 1 over 1, plot point. Take a ruler, put a dashed line through there. And you have the graph of that linear equation y equals x. Now we need to make a determination. Do we shade the plane below and to the right or above and to the left? To answer that question, we need to test out a test point in y in the second inequality, y greater than x. 0, 0 is not available. We have to choose some other point. I'm going to choose 2, 0. So I'm going to test out 2, 0 in the second inequality that says y is greater than x. To do that, we replace the x variable with 0, the y variable with the x coordinate of the x variable with the x coordinate of 2. Is 0 greater than 2? True or false? False. So therefore 2, 0 is not a solution of y greater than x. Being the case, ladies and gentlemen, we shade the plane that does not contain 2, 0 because 2, 0 is not a solution. So therefore, since 2, 0 is not a solution, we don't shade the plane below and to the right of this dashed line because that plane contains 2, 0. We got to shade the plane above and to the left. So here we go. We shade the plane above and to the left. And like I said, this would be a point where colored pencils or markers come in very, very handy. All right. That's the graph of the solution set to the second inequality. We just got one more. Y less than or equal to 4. First, we have to graph the associated equation, which is y equal to 4. What kind of a line is this going to be? Y equals 4.
Horizontal line?
Horizontal line, solid or dashed?
Solid?
solid.
Solid line going right through the y-axis at 4. So we take a ruler, put a solid line right through. All right, that is the graph of y equals 4. And one last move now is we have to determine, do we shade the plane below the solid horizontal line or above? To answer that question, we have to test out a convenient test point in the third inequality. Notice 0, 0 is available. And so therefore testing 0, 0 in y less than or equal to 4 is 0, 0 a solution. Replace the y variable with 0. Is 0 less than or equal to 4? True or false? That's true. So we discovered that 0, 0 is a solution to y less than or equal to 4. So ladies and gentlemen, that being the case, we have to shade the plane that contains 0, 0. Which means we shade the plane below the horizontal solid line because that's the plane that contains 0, 0. So we shade below. And you're looking at the graph of the third and final inequality in that system. I have a question. Where do all these shaded regions overlap, ladies and gentlemen? That's why colored pencils would come in handy here. You can clearly see that all the shaded regions overlap what? Inside the parabolic branches. Wait a minute here. Careful. All the shaded regions overlap inside the parabolic branches, bounded above by y equals 4 and bounded below by y equal to x. You cannot go below y equals x, ladies and gentlemen. So you are looking at the graph of the solution set of that system of 3 inequalities in 2 unknowns. Any point that lies in this darkened shaded region would be a solution to this entire system of 3 inequalities. Okay?
Oh
Yeah.
wait, wouldn't the anything that's above the y equals 4?
Wait a minute.
wouldn't
Yeah, no,
that
you're
be
right.
there?
Yeah, I should not be shading above the y equals 4, that horizontal line. You are correct. I need to get rid of that. So this is not included. You are correct. We got to get rid of that. So this all has to go. So ladies and gentlemen, you are looking at the solution set to this system of 3 linear inequalities and 3 unknowns. It would literally be the shaded region that is bounded above by y equals 4, bounded to the left and right by the parabolic branches, and bounded below by y equals x. Okay, it's got to be in there. All right, and there you go. And we're done. Yep. So that would be the graph of the solution set to that system of 3 inequalities in 2 unknowns. It's quite a procedure, isn't it? Time consuming. You can see it just takes time to solve these systems, ladies and gentlemen, of inequalities. It just takes time because graphing slows us down too. But it can be done. All right, it can be done. I have a question, ladies and gentlemen. Do you think that you can apply these systems to the real world? The answer is absolutely yes. Let's go on down, try to apply this. Here we go. Number 74 is a beauty. It says the coordinate system is placed at the center of a town with the positive x-axis pointing east and the positive y-axis pointing north. A cell tower is located 4 miles west and 5 miles north of the origin. If the tower is 8 mile, if the cell tower has an 8 mile range, write an inequality that represents the points on the map serviced by this tower. Can a resident 5 miles east of the center of town get a signal from this tower? We're going to try to solve this cell phone tower problem, ladies and gentlemen. This is just one little snippet as to where these any systems of inequalities can be used in the real world. The next section, unfortunately, of which we're not covering, is involving linear programming. And linear programming is an application of these systems of inequalities that can solve all types of problems in the business world and in the industry, ladies and gentlemen. Linear programming, okay? I took a whole course at a university in linear programming modeling, okay? So trust you me when I say these systems can be applied to the real world. They can be. Big time, okay? If you don't believe me, just look at the next section, 5, 6 at your leisure. You'll see how they apply them to realistic problems. All right, problem number 74. Coordinate system is placed at the center of a town. So what does that mean, ladies and gentlemen? At the center of town? Well,
The origin.
what that means is the center of town is at the origin. We will assume ground zero for this town is literally at the origin. Now, positive x-axis points east, y-axis positive y points north. Cell tower is located 4 miles west and 5 miles north of the origin. 4 miles west, 5 miles north. So if the center of town is at the origin, what was that again, that cell tower? Was it 4 west, 5 north, or was it 5
Yeah.
west?
4 west, 5 north.
4 west, 5 north. 1, 2, 3, 4, 4 west, and then 5 north. 1, 2, 3, 4, 5, right here. All right, there's the cell phone tower in relation to the center of the city, which is at the origin. Cell phone tower is northwest of the center of the city. You can see that because this is north, this is east, etc. Okay. All right, there's the cell phone tower, ladies and gentlemen. Now, what was the range of this cell phone signal from the tower? The range.
8 miles.
8 miles. Ladies and gentlemen, if the signal has an 8-mile range, do you agree that that would be the radius from the tower that the signal can be, accessed? So the range is 8 miles from the tower. So this signal reaches out 8 miles in all directions around this tower. And therefore, ladies and gentlemen, do you agree the inequality that would model, okay, the signal of this cell phone tower would be in the form of a what? It would be in the form of a circle inequality. Do you agree? What is the center of this cell phone tower? What's the location of this? It's -4, what, 5? -4, 5. Let's write the equation of the circle that has a radius of 8. The range is the radius of the circle of the cell phone signal. So therefore, the equation of our circle is going to be x minus h squared plus y minus k squared equal to the radius squared. That's going to be the equation of our circle. So it's going to be x minus, what's the x coordinate? -4. So x minus a -4 squared. Y minus the y coordinate of the center of the circle is 5 squared, and that's equal to the radius squared, the radius being 8 miles. The square of 8 is 64. So therefore, x plus 4 squared plus y minus 5 squared equal to 64. Ladies and gentlemen, that would be a circle, okay, that is around this, the center of this circle, which is the tower, whereby the signal would reach out to. So 8 miles from the center, 1, 2, 3, 4, 5, 6, 7, 8. The circle would contain this point. 8 to the right, 1, 2, 3, 4, 5, 6, 7, 8. It would contain that point, etc., etc. So I got to try to draw this now and wish me luck. Boy, that's not bad for freehanding it. Look at that. That's one of the best circles I've ever drawn. So ladies and gentlemen, the signal from the cell phone tower would reach out as far as the what? As far as this circle goes around the center. I obviously don't have my circle drawn to the left accurately, but you get the idea. The signal from the cell phone tower would reach out. So any home that's found within the circle, ladies and gentlemen, would be able to receive the signal. Any home or place that's outside the circle would not be able to receive this signal. So what inequality, ladies and gentlemen, would represent, what inequality would I write that would represent where the signal can be reached by a home? Do you agree the inequality would be x plus 4 squared plus y minus 5 squared less than or equal to what? 64? You agree? And the solution set to this inequality would be any point that either lies what? On the circular boundary or inside. So ladies and gentlemen, any home again that lies within the circle or on the boundary of the circle would be able to receive reception, would be able to get the signal from this tower. Any home that's outside the circle is not going to have access to this signal. All right. Now, what was that other question they asked us? There was another question. It said, can a resident 5 miles east of the center of town get a signal from this tower? 5 miles east. Well, they're gonna be out here, 1 mile, 2 miles, 3 miles, 4 miles, 5 miles. Ladies and gentlemen, are they gonna be able to get the signal? 5 miles east of town? They're not gonna get the signal, are they? It's not gonna happen. So ladies and gentlemen, the answer is no. Place located 5 miles east of town, town being at the origin, would not get the signal. There you go. There's your answer. As long as you're inside the circle around the boundary, you'll be able to get that signal. If you're outside, you're not gonna get it. So. You know, cell phone towers not only emit a signal, ladies and gentlemen, literally in a circular fashion, but they basically emit a signal in a spherical fashion around the center of the antenna. Spherical. So this circle would actually come up off the ground. You know what I'm saying? And its radius would also be 8 miles above the ground. Isn't that cool? All right. All right. Okay, so what we accomplished in this section, ladies and gentlemen, is we learned how to solve inequalities in two variables. And we also learned how to solve systems of inequalities in two variables, in both cases by graphing the solution set in the XY plane. I have made available the Chapter 5 quiz. You should have more than enough time on the quiz. You get 2 takes on the quiz. I'll take the highest of the 2 scores. I did also enable a feature on the quiz that enables you to look at examples for problems that you might be stumped on, which it's the first time I enabled that feature. I decided to do that. And for that reason, you should have more than enough great opportunity to get a good grade on this quiz. All right. All right. So with that, I'm going to let you go. You guys have a great day. I will update the homework for 5-5. And hopefully I'll see you on Wednesday, ladies and gentlemen. 1 week, almost 1 week away from Thanksgiving already. Well, I can taste that turkey and cranberries already. You guys have a great day. I'll stay on the line for questions.